Okay. All right. So Eliza is going to talk to us today about quantum teleportation. She's going to give us an introduction to the topic. She is an expert in this topic, I'm told by Marguerite, which is amazing. Yeah, take it away, Eliza.
All right. Hi, guys. So first of all, with quantum teleportation, since it's a quantum communication protocol, I just thought it was appropriate to go over how we communicate today with our regular internet and this thing. Okay, yeah. So how does our internet work today? So say you are logged on with a computer that has a certain IP address, which is your internet protocol address. And this basically just separates you from everyone else that's logged onto the internet. It just gives you like an ID. And say you like wanted to send a message to your friend, like, hey, dude. And so this is going to happen by your computer sending out these digital signals and your modem plus router converting those digital signals to electronic signals being sent through wires to the internet. And then the internet, I didn't show it the infrastructure inside because it's so complex, but it basically has these kind of router things that routes your data packets. So your data is your message is going to be basically broken up into these packets of data, and these packets of data are going to be routed to your friend's modem, and this modem is going to convert it back to digital signals, and your friend is going to get your message. So these the internet makes sure that it actually gets to the right IP address. So this is classical communication. Now, ideally, you would want quantum information to work the same way, right? You want to be able to send it through the air or through wires or whatever. Unfortunately, it doesn't work like that. So qubits are the information bearers of quantum information, and they can take the physical representation of photons, ions, electrons, atoms, all these subatomic molecules. And the problem is these molecules, they're very fragile, meaning they can, for one, if you try to send them inside a wire, they can knock into like within the wire walls and they can just get corrupted right away. Like your information is basically going to get destroyed. Or they can also get absorbed in the optic cables as well. And if you try to send them through like free space or just through the air, they're just going to, bump into other particles in the air as well. So, just directly sending photons, ions, full of your information, it's not going to work. So what do we do now? So this is where quantum teleportation came in. So the main advantage with quantum teleportation is that it allowed quantum states and quantum information to be sent to other parties without the actual particles and information physically, like without the actual particles that have the information inside them physically leaving the party that wants to send it. So before I get into this protocol is going to make very big use of something called quantum entanglement. So if you recall Marguerite's explanation of quantum entanglement, basically, I'm going to go through an example that a very big quantum head known as John Preskill came up with to explain quantum entanglement. So if you have a classical book, let's say you have a classical book, intuitively, you could read every page of that book and put all that information together to get the main message out of the book, right? But in a quantum book, you can't do that. So say you had a quantum book with all the pages entangled with one another. If you try to reach an individual page, you're going to get random gibberish out of that, or it's just going to be a blank page. But in some way, you have to read all the pages together to get the information or the main idea out of the book. So in a way, the information is not contained within the pages, but it's contained in the correlations between the pages. Okay, so that's what makes like quantum entanglement so strong, that it's not like you cannot describe two entangled particles individually. Their state has to be described together. And if you try to split them up, you're just going to get random stuff out of there, random information. Okay, so now onto the quantum teleportation protocol. So the protocol is as follows. First, Alice and Bob in the beginning, they share an entangled pair of qubits. So Alice has one qubit over here. Do you see my mouse?
Yes.
Yes.
Okay, good. So Alice has one qubit and Bob has the other down here. So now Alice wants to send a quantum state psi A to Bob. But of course, she cannot directly transmit it through a wire. It would mess it up. So what she does is she makes a measurement on the state that she wants to send and her half of the entangled pair. So just this wire only. And after making that measurement, she gets two classical outcomes. All right. So over here, she makes a measurement on her qubit that she wants to send over, and she gets either a 0 or 1, just a classical bit. And then also down here, she makes a measurement on her half of the entangled pair, and she gets two classical outcomes, 0 or 1. Now, she has those two classical outcomes, each of which can be 0 or 1, and she sends them over to Bob. Now, Bob, he has his other half of the entangled pair. And now based on the results of Alice's measurements, or what classical outcome she sends over to him, he's going to perform correction operations on his half of the entangled pair to recover the original quantum state psi that Alice was trying to send along. Alice was trying to send all along, sorry. So, for example, if Alice were to make a measurement and send the two classical states 0, 0 to Bob, Bob wouldn't have to make any sort of correction operations on his half of the entangled pair in order to recover the original quantum state. But, for example, if she had gotten 0, 1, it's like 0 for M2 and 1 for M1, he would have to perform the X operation on his half of the entangled pair to recover the state. If she got 1, 0, he would have to perform a Z operation on his half to recover the state. And if she got 1, 1, he would have to perform X and the Z operations on his half to recover the state. So yeah, so this is basically, Marguerite, do you think I should go through the math for this or no?
I'm sure.
Oh,
No?
Is it us?
hey.
Okay.
Okay, did you freeze for anyone else or was it just us?
I don't really know.
You didn't freeze for me.
Okay. All right.
Never mind, continue.
Yeah. Sorry.
Okay. So I was just asking, like, if you want me to go through the math, I will. Otherwise, I can skip it.
Yeah, we could go through the math. I mean, how much? There isn't really much more other than the math, is there?
Yeah. So, like, after I explained the protocol, I was gonna get through applications. So that's about it. Yeah.
Okay. Let's see. I mean, we're gonna do like a linear algebra introduction later on. Okay, maybe just like briefly go through it and then go ahead to the applications.
Okay. So Alice Alice starts off with this initial state psi 0. Let me see if I can pull up a laser pointer. Yeah. So she has her state psi that she wants to transmit, and she has an entangled pair of particles as well. So this is like the joint state between the state she's trying to send and the entangled pair. And this is how it's written. So if you like expand all of this, if you write this together, this is how the state is going to look. And then she performs a C naught operation on A1 and A2. So if you go back, you can see like she has 2 qubits, and this is A1, the state she's trying to send, and A2 is her half of the entangled bell pair. Okay. So after she performed the C naught operation, you know what? I'm going to back up right quick. I feel like I want to explain this. So she has psi A, which can be written as alpha 0 plus beta 1. And she has a tensored, or like together with the entangled bell pair, which is written as 1 over square root of 2, 0A, 0B plus 1A, 1B, because Alice has half of it and Bob has the other half. Now, writing it together is basically foiling it. So you take one term here, you multiply it in a way over here. You take alpha 0A, multiply it here with 1A, 1B. Same here, beta 1A multiplied with 0A, 0B, beta 1A multiplied with 1A, 1B. And this is ultimately what you get as the state. Now, Alice then performs a C naught operation on her half of the qubits, so A1 and A2. So A1 is the state she's trying to send, A2 is her half of the EPR pair, and what the C naught operation does is it looks at the control qubit and sees if it's in state 1, then it flips the state of the second qubit. So in this case, if Alice's first qubit is in state 1 anywhere, then this Alice's second qubit will be flipped. So you can see that here. Since Alice's first qubit over here was just 0, this part of the expression didn't change. But then down here, Alice's first qubit is in state 1. So Alice's second qubit became 1 over here, and Alice's second qubit became 0 over here. Okay. And then she applies a Hadamard operation on her first qubit, so the state she's trying to send over. So basically, you're going to turn the 0 state here and the 1 state here and apply like a Hadamard operation on both of them. So this is just what I did here. The Hadamard operation basically puts the 0 state into a superposition. Let me see if I can write it down. So the 0 state, if you recall, gets sent to 1 over square root of 2, 0 plus 1. And for like the minus state, for the 1 state, it gets sent to the minus state, which is 1 over square root of 2, 0, minus 1. So that's basically what I did here. I expanded this into its superpositioned state. All right. And once you like write this out, meaning like foiling and regrouping terms. So again, foiling this with this and this with this, and you write it out like this, you can clearly see what I was talking about before. So over here, this is the state that Alice gets from her measurement. And then over here, you can see this is the state that Bob will get on his half of the entangled pair once she makes that measurement. So if she gets 0, 0, Bob doesn't have to do any correction operations. If she gets 0, 1, the Bob has to apply an, an X operation on his qubit. So the X operation would basically take 1 to 0 and 0 to 1, and boom, you have your original state back. If she had 1, 0 as her measurement results, then Bob would have to perform a Z operation. And the Z operation basically takes the 0 state to the 0 state, but it takes the 1 state to the negative 1 state. So over here, you can see if she performs a Z operation on here, this will just stay 0, and this will become plus 1, getting you back to your state. And if she has 1, 1 as her result, then he would have to perform the X operation, then the Z operation to recover the original state. Okay. Any questions so far? No? Okay, great. Let me check the chat. Okay, great. So I can't seem to flip. There we go. So now that we've learned about quantum teleportation, I want to go through some applications for it because it's a very powerful protocol and it's something that's used in a lot of quantum algorithms today. So first is like entanglement swapping. Now, entanglement swapping is just a way to distribute entanglement between, two parties that are far apart. So say you had Alice, Bob, and Carol, and Alice and Bob shared a pair of entangled qubits, which are the two circles, and Bob and Carol also shared a pair of entangled qubits, which are the two stars. Now, the goal is to have Alice and Carol basically entangled with one another, or have their qubits entangled with one another. How are you going to do that? Well, Bob, what he can do is he can perform a measurement, something called a Bell measurement, on his two qubits that he has in his possession. Now, recall, this state that's in this qubit is basically the state that's entangled with Alice's qubit right here. Okay? And so by performing the Bell measurement, he's basically performing quantum teleportation. Yeah, he's basically performing quantum teleportation. Okay, so the state, Alice's entangled state, is basically coming over here to the star. Okay. Wait, just give me 1 second. Did I get that right? Yeah. Yeah. So, sorry, no. By performing the Bell measurement here, the state that's in here that's entangled with Alice's qubit gets sent to Carol's qubit. Sorry, this is what quantum teleportation is right here, because you have two pairs of entangled qubits, you have the state that you want to transmit, and it's being transmitted to Carol. Okay, so now Carol has the state that Alice's qubit is entangled with on her qubit. So now indirectly, Alice and Carol are entangled with one another without ever interacting with one another. Okay, so in a way, using teleportation, you basically distributed entanglement between two parties that are separated. They're basically far apart. Okay, so why do we want to use entanglement swapping in the first place? So this plays into a very larger picture known as quantum networking. So, in a quantum network, you basically have a bunch of quantum computers that you want to be able to talk to one another. So how are you going to get them all connected? You're going to get them all connected using entanglement swapping. So this is basically a protocol that was described in a paper of mine. So say you have two parties, Alice and Bob, and Alice wants to become connected with Bob. So you're going to basically do entanglement swapping. So right now, Alice or the repeater or Bob, they don't have any pair of entangled qubits. So for that, you need source station. So in between every node in the network, you're going to have this source station that's going to generate a pair of entangled particles or qubits. And then they're going to be sent to Alice and the repeater. And over here, this is going to be sending it to the repeater and Bob. Okay. Now, once that happens, what the repeater is going to do is it's going to perform a Bell measurement on this qubit. And remember, this qubit has the state that's entangled with Alice's qubit in it. Okay. And it's going to transfer this to this star. And this star is basically a quantum memory. And the quantum memory is going to store that quantum state for a certain amount of time. And now the same thing happens here. this qubit has the state that's entangled with Bob's qubit over here. And this state is going to be transferred to this quantum memory via the Bell measurement. All right. So now that we have it in the quantum memories, yeah, so this contains state with, yeah. So now that you have it in the quantum memories, you can perform a Bell measurement, or the repeater is going to perform a Bell measurement on both of the quantum memories, and it's going to send the state that contains, or the state that's entangled with Alice's qubit to Bob, ultimately entangling Alice and Bob's qubit. So this is just entanglement swapping happening here, but with an addition of quantum memories. Okay, so now that Alice and Bob are connected with one another, Alice can send whatever state she wants to Bob, no problem. And this is going to happen at every single node until all of the computers, all of the nodes are connected with one another. And this is going to form our quantum network, or our quantum internet. Now you may be asking, like, why do we need quantum memories, blah, blah, blah. Why can't we just do teleportation like directly? Why are we storing it in these extra stars? Well, the distribution of entangled qubits is probabilistic. So you have all these links in a network, and it's not guaranteed that these entangled pair of particles are going to arrive at the nodes. Okay, so let's say these pairs of entangled particles arrived at the Alice and the repeater, but over here it failed. Either the qubits got lost, or they got absorbed in the optical fiber. So if that happened here, then the state that was here, or the qubits that are here, they would just go to waste, because with time they just get corrupted and they decay. So it's necessary to have a quantum memory to store the state, just in case this link doesn't, happen, or these photons don't arrive at their destinations in time. Okay, so this is retried a bunch of times, and meanwhile this is stored for safekeeping, the state here. Okay, so this is a pretty big application. You can see how quantum teleportation is embedded into this huge application of quantum networking, and basically is a major tool in the quantum internet. Okay. So yeah, so other applications for the quantum teleportation can include quantum key distribution. I just described quantum networking, and you'll see that it's used in many quantum algorithms that we're going to study. All right, I think that was it. Yeah, any questions?
I think Roy has a question in the chat.
Yeah. Advantage of a network versus plain teleportation. So I mean, in a quantum network, you're going to have multiple parties being able to communicate with one another, as opposed to just two people. So that's why we want a whole network of these connections happening. So the way I describe entanglement swapping is how multiple parties can be entangled with one another. It just doesn't have to be two parties. So this is why entanglement swapping is so useful, because you're distributing entanglement between multiple parties. Kind of like a decentralized network of teleportation. Sorry, can you elaborate on what you mean by that? Feel free to unmute.
Sorry. So I don't know if you would know much about decentralized internet or that kind of stuff, but sort of how I guess an equivalent example would be how Bitcoin has ledgers and everyone has a copy of it, and you can sort of like balance them out? Is it sort of a similar thing where you basically like have this like a balance of teleportation swapping? I'm sorry if I don't make much sense.
Uh, hmm.
Is he talking about like if you have like a network where one node goes down, it doesn't necessarily take down the whole network? That sort of decentralized network?
Oh, okay.
I don't know if that's what he meant, but
Oh, are you saying like if one of the nodes of the network like malfunctioned or something, it would take down the entire network?
Yeah, sort of. Yeah.
So yeah, well, no. This is fail proof for that. And yeah, so basically just like in communication today, it wouldn't no, it wouldn't do that. No. So I'm pretty sure like no, it wouldn't affect it if like one node came down, because we studied that in my work. We basically tested the robustness of architectures, and we were like, okay, if one node malfunctions or two nodes malfunction, how will that affect the whole network of entangled nodes? And just one or two nodes, it wouldn't make a difference. But as soon as you hit like 25% or 50% of the entire network, then yeah, that's gonna have an effect. And the main reason, like in malfunctioning, the only way this could malfunction is if the qubits don't arrive at their stations. And this is why we have the quantum memories to kind of store those quantum states for the time being until the rest of the connections are established. Okay, but if they're not, you indeed do have to restart the protocol. If they're not established in time and the quantum state in the memories like decays or just gets corrupted, you do have to restart the entire protocol. That's true. I hope that made sense.
All right. Do you have any other questions? Oh, Roy.
Yeah.
It looks like Roy has one in the chat as well. How does a network work after one party has made a measurement?
This question. Data words from your.
and then Alex asked another question jumping off of Roy's. Does it get updated outwards from the nearest nodes? So I guess somebody makes a measurement at their node using their entangled bit. What happens?
Hold on, let me go back. I can't seem to go back. Okay. Party has made a measurement.
These questions are open for discussion, by the way, guys.
Yeah, like let me think on that because that's interesting.
Yeah, I'd be interested in the answer to that as well. You know, you make a measurement, it obviously collapses the wave function of the entangled pair. So how does that affect the network? You know, let's see. So Roy's question, and then Alex. Yeah.
Don't apologize. We're all discussing together, right?
Yeah. But we're not trying to drill you, Lisa.
Yeah, no, it's fine. Like I'm honestly the other things I've so I think maybe it's like we're getting confused. Like, yeah, you're true. It's true that it collapses the wave function. So basically when the repeater, which is the middle node, makes a measurement, it doesn't like collapse the entanglement, but it actually, transfers it to the other party, Bob. So basically when the repeater makes a measurement on the the 2 qubits here, it basically sends this state over here to this quantum memory via the teleportation protocol. So again, you're making a measurement, you're getting classical outcomes. Based on those classical outcomes, you have to perform correction operations to, recover the original quantum state, and you have to put it in that memory. Okay. And that quantum state is like the state that's shared, like the state that's entangled with Alice's qubit state, basically. So in quantum teleportation, when you make a measurement, it's not like it's collapsing or ruining the state that you want to send. It's in a sense transferring it to your other party via this measurement. Okay, via this measurement and the correction operations. So no, it doesn't like collapse. Does that make sense?
I think so, yeah. I guess the question might have been more like, so when after the state is transferred, well, no.
Are you saying like
Yeah.
after the state's transferred and they want to use it for something now?
Yeah, no, it's no longer entangled, so that's.
Well, no,
that's-
it's no longer entangled in principle, but the network distributes entanglement, so it can be entangled,
Okay,
right? So yeah, they have entangled bits at the end, at all their nodes at the end of the distribution, and I guess now they want to use it for something.
so Mary Catherine had a more application side question. So has the network scale any limitations on the software side, or is it mainly on the hardware side?
Well, mainly on I feel like it would be the hardware side. Definitely like the more nodes you have, the more you have to like make sure that all of the connections are established. So that's like a limitation. Like the distance that the nodes are like separated in between. Like if the repeaters and all like the nodes have a large distance in between them, and the entangled particles from the sources have to go like large distances to get to the nodes. God. Let me go back. So yeah, so if the distance between these nodes is very large, then it could affect whether your photons actually arrive, because the larger the distance is, like the chance of the photon arriving decays exponentially with the distance. Okay, so that's another limitation. I don't think there's a software limitation, but then again, I don't think we studied that in this work. We only studied like physical limitations on the optics side.
Yeah, I was just curious because I've only heard of limitations on the hardware side. And I've never heard of any type of limiting factor on the software side. So I wanted to see if y'all knew of any of those instances, but I don't think there would be any way for that to happen, right?
Yeah, no, I mean, like you could have a maybe malfunctioning in the optical devices that do the bell measurement in the repeaters. That could be something. But that's mainly like a tech fault. Again, hardware. No, I don't really see a software limitation right now from like this protocol. So keep in mind, this is just one protocol out of like many other quantum networking protocols. So I'm biased against this one because this is the one I worked with. But there are many others, and I'm pretty sure there are many other papers extending from my paper that have perfected or improved this protocol. So yeah, I was just showing you that there is like an like how teleportation is embedded in like simple or like these larger applications like quantum networking.
Thanks.
Okay, I have a question. So,
Yeah.
right now, we don't have a repeater, correct? Is there any form of repeater that it like exists or can be implemented, like any model that you know of?
I think like 2 years after this paper came out, someone had come up with a repeater model.
Interesting.
Yeah, they did. And I don't recall the paper's name right now, but I remember talking about it with Sumit. So yeah, so I feel like there's definitely a model for both like a quantum memory and a repeater.
Any other questions for Eliza?
Have you worked only in, I guess this is like an overall question. I'm just curious, like, are you guys mainly interested in like solely optics, or have y'all dabbled in like superconducting qubits, like cold ion, whatever?
Well, are you talking to me specifically or?
Yeah, you
Oh.
and everyone else. I'm just curious.
So no, I have not. Well, if you mean superconducting, I have worked with IBM's Q experience and work with them as well. But mainly, I feel like I've worked with photons as like my qubit representation, mostly. Like I haven't worked with ions or ion trapped.
Okay. Any other questions? All right. Thanks, Eliza, for the talk. It was fantastic.
Thank you.
Let me stop this.
I hope you guys know about teleportation now.